Computers don't tolerate ambiguity. Computers can't tolerate ambiguity, and ambiguity is a very bad thing for computer programming. Everything should get well defined in computer science. Well formed formula means well formed formula, and formula is well formed means there is no ambiguity, no error. Now, while we are trying to implement the automation and artificial intelligence and unsupervised learning is necessary, then we need the dataset to train the objects such that we can generate the theorems from the trigonometry expressions or the objects like this. Suppose we have this need for the datasets, then we will get the dataset for the theorem generation from here in Autodesk. There's a 2019 repository, and from where you can get the dataset, and this is saying that the total dataset is like this, and where the dataset has the meaningful column names. Let's describe the things here, and you will get the dataset here and also the simulator here. From the bottom of this you will get the same simulator here from this zip, and with this you can get the dataset also in the D drive. It will automatically saved in the D drive, where you can train the machines with that dataset. You can train the machines to generate the theorems for trigonometry expressions, and every of the line segments generated through the simulator has a meaning. We should demonstrate it here. Like we have already said that cos theta has 4 symmetries A, B, C, D, sin theta has 4 symmetries E, F, G, H, tan theta has 4 symmetries I, J, K, M. L is already booked as the initial line segment, which is 1. Sec theta has 4 symmetries like N, O, P, Q. Cosec theta has 4 symmetries like R, S, T, U. Cot theta has 4 symmetries like V, W, X, Y. And trigonometry expressions are very abstract, which contains one-to-many relationship, means one trigonometry expression can have many geometric possibilities and all are valid, and the numerical values of the trigonometry expression represent the output line segments as the length, and that length value is the evaluation of the trigonometry expression. But when we try to draw the geometries, then there are multiple valid possibilities of bunch of line segments, and all the bunch of line segments depict the same trigonometry expression and all are valid, but some of these bunch of line segments can depict a bridge, and the other bunch of line segment can depict the floor plan, and other bunch of line segment can depict the town planning. So single trigonometry expression can represent the multiple bunch of line segments, BOLS object, BOLS, that is the bunch of line segments, and we can create the triangles in the 8 different orientations, and that we have already described here. And Z is like the army calling over, like my part of task is done, now the next operation should start. Suppose every trigonometry expression is rewritten with the geometry parsers, and then the conversions is done like this. LAZ means 1 cos theta is constructed, LAOZ means cos theta and sec theta is multiplied, and then final output is constructed. Z means the, now my part of the gluing or the other plus minus into divide is completed. Now you can take the output. That Z means this instruction to the computer, because ambiguity is not allowed in computer science. L means the initial line segment, and any kind of the GT terms or the GT simplex or the GT locked set are constructed from the same line segment. L, initial line segment L, and then multiple operators are multiplied, and then the final output line segment is generated, which is instructed here to the computer as Z. Like when we press enter, that is the command, then we say that my command text is completed. Now enter means you start processing. So for every operator in the algebraic operator or arithmetic operator, L, A, B, C, D, whatever is there, then the L is the initial line segment which is taken, and the Z is the my part of the operation is done. Then next plus minus into divide you can start. This is the instruction to the computer that the Z means one part is complete, now next operator is to start. And these kind of things, that means AO, 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 which means that cos theta and sec theta are multiplied, and ultimately it is becoming 1, but it is going to describe you a 1 to the power n is not actually 1, it is a geometry, and there are multiple possible geometries are there. And the data set is expressed here in this way, and the column names are described here. In this site you will get this understanding, and you are seeing the site here, and from this site you can see the demonstration that how the data sets are described here, and the data set has the geometry here. I will show you the geometry. This geometry is generated from the simulator. I am trying to show you the non-ambiguous constructions here in this geometry. Now every geometry shapes can have a music, and you are listening that kind of music here, which is odd kind of music, but we can get the beautiful music also. And these are the grammar for the ear, which depicts the geometry representation to the ear. Now coming to the part of the data set. Now you will get the data set here, and I'm showing the data set which will automatically save in the D drive when you will run the Geometrifying Trigonometry simulator. These parts are corrected now, and 0 to 1 values are done. Every line segment has an address, expression classifier degrees with the 45 degrees shown here, and A 6 times or 1 times is used. O is the sec theta which is used how many times, and these are demonstrated here. The expression in degrees, how many times A, how many times E, these are the complement of the line segments which are also shown here. Now the seed angles, and which are the signed gradient for everything. There are the gradients are necessary to construct it on the scaled geometry on the CAD, such that we can import it into Tekla or import it into the Revit, so that we can get the floor plans automatically there. Those are the bunch of line segments actually, and we put the profile values there, and then we will get there. The command characters are like these, and which are cos theta, sin theta, sec theta. These are the command characters or any kind of values there. And the orientation characters I will describe you here with the animated geometries which are automatically constructed in the simulator. The seed angle values and which are there, and current given segment and what kind of data is consumed, as it is consumed as the hypotenuse or consumed as a base or consumed as a perpendicular, that is written here. That is necessary for the machine learning systems. We convert the things into numerical values when we are converting it into the proper machine learning things. And current output line segment is base. It is consuming the hypotenuse and constructing the base, and the complement is the perpendicular. So these three ultimately makes the triangle, and then we are trying to generate the xy values, and with which we construct the triangles there. These values will come here, and with these outputs we generate the constructions, and finally we can train a machine to generate the theorems for the plus minus into divide everything. And here the columns are shown, the column names which store the coordinates of every points. The pivot, stage and nodal points are changing, revising every time. For this expression for which the data is kept here is not showing the pivot because all are 0 0 0. For the other kind of simulation you will get these values, and in this way you get the columns here, and these are the given sequential recursive construction which are like these, and output line segments are like these, where the complement line segments have the address like this. For A the complement is E, for O the complement is J. in that way. That is already described here in the next part of the videos here, where I'm just showing here the demonstration for the data set, how to read it and how to understand it. And for every command sequence, these are constructing the line segments and constructing the triangles, and the construction protocol has the orientation also, the triangle construction orientations. There are 8 possible orientations, and those possible orientations we will describe here. And for the zoom to fit, we need the AABB minimum and AABB maximum points. AABB means actually aligned bounding boxes. And these are technical terms for the building information modeling. Now cumulative recursive frame regions are there. Now number of cos powers, number of sine powers used here when we are constructing these geometries, that is also stored in the theorem generator system, so that we can design the theorems here. And the columns, we can extend it as more people will get involved into the simulator designing. We can extend these things to train the machine with more number of data, so that we can generate more number of theorems there. Now this part is demonstrated here. Now we will demonstrate how to think about these things. The AABB is here, and the command string is there in the row number 18. It is the command here. Now it is showing so many information here. We can clean these informations first, so that we can put the data there. These are the demonstration for these texts to show here. Let's keep these there. Now we can remove these things. These are the cumulative summations, not forcing for collinearization. These are just cumulative adding the things, and those are also very helpful for different kind of theorem generation. So we will show those things later on. We are cleaning the screen, opting that we don't need these things there. We can opt for these, so that we will not save the data in the drive. This is for the DXF generation with the true scale, so that we can import the data into the Tekla or Revit or in CAD to generate our engineering purpose things, or for the robot planning, robot arms planning also. Now we can put it no, so that we will not generate the scales here. It is just to demonstrate here. Now for everything you can see the bounding boxes. That is the AABB corners, that is the actually aligned bounding boxes. We can take the OBB also, that is the object bounding boxes. That is the complicated thing. We will show it later on. Here these are like this, and we are stopping all the jungles here, so that we can see the clean geometry. And then we can stop many other things also, so that we can get the cleaner geometry here. Accumulated points for the dots enlarged. Okay, no. Taking it, no. Slider scale factor, no. We can stop all the circle constructions. Here the in-circles, circumcircles, orthocircles, and several large number of circles possibilities are there, which we can generate for the machine learning and theorem generation and data accumulation, theorem planning that we can do. We can stop all these things to understand the things, the lesser jungles. You can see the screen is getting cleaner, and with these lesser geometries present there, we can see the things more clearly. Now we will make this data also clean. These circles are coming here because we have special highlighting centers. No, we can. Do you need the special highlighting of the centers? No, we have said it here. Now we can ask that we do not need the circle, circumcircle, also circle. So it is showing now. No. Now output line segment thickness is say 11. The complement line segment say 6, and the given line segment say 3. Now we can see these things here, and to show the circumcircle, circumcenter 11, 6, and we can show the thick output. Yes. Then we will get the thick outputs here. Now here we have seen that the LAOZ, which means the cos theta, L into cos theta, then L into cos theta into sec theta, then cos theta into sec theta into cos theta. Ultimately we are getting 1, and for theta is almost 0, we will get it almost a circle, and we will get almost a circle there. If the value of theta is almost 0, then we will get the circle there, and we are seeing the address of this. Now we can make the construction protocol like this. First triangle is made, then it is glued with the second triangle, then it is glued with the third triangle, and in this way you can see that the construction is completing and GT simplex is constructed. Now if we think that this is a particular orientation here, and if we want to change the orientation of the construction, instead of the raw construction orientation, if we want to construct all the triangles anti-clockwise, then we will get this output, and all the triangles are constructed anti-clockwise, so we are getting this output. And if we want to construct all the triangles clockwise, then we will get the output like this, where you can see the gluing nature of the construction. Say for all the clockwise constructions, the gluing natures are like this, and so everything overlaps on a single line segment. If we take one anti-clock, second one clock, then we will get this output, that is, it will shuffle like this. And if we talk it as a first clockwise then anti-clockwise, then we will get the output like this, and where the construction will generate like this. And if the theta is changed, now its behavior will change like this, and we can save this DXF directly in redrive if we put the yes there. I have already shown you. Now if we consider it as a clock, then one anti-clock, then the construction protocols will change, and the same equation will give you the different geometry. Overall geometry will change, and it will have the different behaviors here. Now if you want to see the cumulative summation of these output line segments, then we can make this yes, the summation behaviors which are non-forcefully straightened, and the summation line segments will show in the cyan, and the summation of the complements will show in the dark magenta. In this way we can think about the construction of the cos theta into sec theta whole to the power n, that is 1. The numerical value evaluation will give you 1, but geometric representation will give you multiple different possibilities here, and all of these possibilities will just change. And if you want to see the sequential construction of this GT simplex, then you can check it in this way, that the sequential gluing are occurring here, and with this sequential gluing you can get the whole geometry after the construction. The deep blue line is the output line segment, the deep red line is the complement line segment, and in this way we can check the output conditions. Now output and the zoom to fit is automatically working, and we have already taken it yes. So the cumulative summation are found here, and it is also a interesting subject. For if we cumulatively sum the hypotenuse, then we will get like this perpendicular hypotenuse. So if we sum the perpendicular cumulation, if we sum the hypotenuse cumulation at every stage, then we will get a different kind of line segment summation, and we can get the interactive behaviors, how this can give you the idea on the theorem planning. Now we will talk about the other kind of cumulations like LAAZ, which is the cos cube theta. Say this is the cos cube theta, and with a one kind of orientation. Now if we take it LAABZ, which is also cos cube theta, and which has a different behavior like this, if we take it LAACZ, then the behavior is like this, which is also cos cube theta, and already said you that computers don't allow ambiguity. So cos cube theta can have multiple varieties: L A B L A A A Z, L A A B Z, L A C Z, L A D Z, and in this way we can get the different kind of possibilities here. With this you can check how it behaves, and with this you can also check the orientation of this triangulation, which can become anti-clock construction, clockwise construction, partially anti-clock, partially clock, and these behaviors will change. The triangle construction behaviors will change. We can take it raw, we can take it swapped output, that is S, and we can talk raw swap, that is first construction is raw, then second one is swapped. We can take it as the first one as anti-clock, then one is clock, then one is clock, then it is behaving like this, and all these possibilities we can check with multiple values of theta, and we can see that a particular line segment is always passing through the midpoint of the first one, and these kind of behaviors are possible. And if you want to change the L rotation, then whole bunch of line segment will change, and with these sliders we can play with the geometries to understand how the things are behaving. Suppose if you want to get the multiple values of the one, that is an interesting thing for the floor planning in the architectural engineering, that is LIJKM is the tan to the power 4 theta, and reverse of the tan is the cot, which is RSTU, which is VWXY, and if we ask to construct the geometry there, then the geometry will behave like this, and for the constructions all the things will be anti-clock, and in this way we can see the behaviors of this construction. The whole geometry construction for a particular value of theta will change if we take it as a raw, if we take all anti-clock, if we take all clock, then the geometric constructions are changing, and the cumulative summations can also change. If we want to see the cumulative summations, you can see the nature of the cumulative summations there. These are like this, and we can see the behavior of these constructions stage wise: first stage, and second one, third construction, fourth, fifth, sixth, and in this way the whole constructions are changing. And if we change the orientations of the construction for every triangle A to anti-clock, then the behavior is changing. Anti-clock clock, then it is changing, and it is anti-clock clock clock, anti-clock clock, anti-clock clock, then the construction is changing again. In this way you can play with the different kind of geometry for the same geometry expression whose numerical value is 1. Interesting thing is the numerical value is always 1, because tan theta into cot theta is going to give you only 1 there. Okay, so here you are understanding the concept. Now the operator precedences are done. Now we will talk about the proving of triangles. We are coming back here with the numerator, denominator. Now numerator is the output line segment, denominator is another line segment, which is the input line segment, and the third line segment comes due to the construction of the additional lines, like the free ends are joined, and in that way we must complete the triangle, and in that way our triangles are generated from the ratios. So stop thinking that ratios are simply a number. Try to think from now that the ratios have the different kind of reasoning, and when we have the numerator 1 divided by denominator 1, and it is multiplied with the numerator 2 with the denominator 2, suppose it is multiplied with numerator 2 with denominator 2, and the multiplication is done, then we will consider there symbols like summation symbols, product symbols, and the integration symbols, differentiation symbols were finalized during 1660 to 1860. So, and matrix came after 1870. So, we should not think that determinant and matrix both came at the same time. Determinant was there during the time of the grammar, but the matrix came after Hamilton and Cayley in 1870. So don't confuse that the things of mathematics were generated in one day. No, it took 2000 years, mainly 2600 years to create these symbols now, and the x and star were taken as the multiplication after the computers came, and slash symbol is taken as the division after computers came. So things evolve and people do new kind of reasoning with a new kind of activities, and new kind of activities are possible when new kind of reasoning comes, and every new kind of reasoning comes with a new kind of symbols and new kind of operators, precedences, new kind of vocabularies also appear, like the pivot point, stretch point, nodal points are very much important in geometrifying trigonometry. And this concept that the input line segment is consumed and output line segment is constructed, and the third line segment, which is the complementary line segment, is also constructed. This kind of new reasoning came after Sanjoy Geometrifying Trigonometry came into the play, and that also came due to the API development, application programming interface developments for the construction industries, for the mechanical engineering problems, to find the visibility searches for the robots, to search for the automated staircase designing, automated roadways planning, automated driverless car movements. These kind of things pushed the application programming interface developers to create new kind of vocabularies and new kind of operators, such that these automations are possible now. And Sanjoy Geometrifying Trigonometry talks with these operators because it is the founding for these kind of trigonometry constructions from the trigonometry expressions, and these kind of requirements were not there before. Automated computational constructions from the trigonometry expressions were necessity for the new kind of needs, and these new kind of needs asked the developers to develop this kind of new kind of vocabularies. Now, when these kind of things are there, then our initial line segment is plugged into the first denominator. Initial line segment, suppose L equal to 1, the initial line segment L equal to initial line segment equal to 1 is plugged in the first ratio here in the first denominator, and then this initial line segment constructs the first denominator. This denominator is consumed through a ratio, and the first numerator line segment is constructed. This first numerator line segment is now consumed into the second denominator, and this second denominator is now the initial line segment for the second ratio, and then the second ratio moves the second triangle there and constructs a new line segment, and this new construction enables a new constructed line segment, which is now the input for the third denominator, and this third denominator is constructing a third line segment. In this way, the process continues, and the playing effects continues. This same kind of thing is also added, means collinear objects are there, and then it forms another addition things. Say we will describe it later on. Suppose this one is another triangulation here and generated from the same line segment, but its triangles are different. Suppose the denominator triangles are different, and we can think of these things like this. Okay, there was a mistake and I'm trying to explain it properly here. Suppose this one is the construction like this, and we can think these kind of objects as the numerator and denominator. Suppose this one is not the output for this and denominator. Suppose the different line segments, say this one is the output of this denominator object. Now when we have the two GT simplexes, say suppose this one is a GT simplex and this one is also a GT simplex, constructed due to the multiplications, pure multiplications, construct GT simplex object, and pure multiplication constructs GT simplex objects in Sanjoy Nath'S Geometrifying Trigonometry. But all of these objects are starting from the same line segment L, and say everywhere these constructions are done from the same line segments L, and this L is transmitted to the output line segments other line segment here, and now this one is the output line segment as the denominator, and this one is the output line segment for the numerator. Say we should do a different color coding here. Suppose this one is the green one and this one is the cyan one. Now we have a denominator bunch of line segment. This is a bunch of line segment balls object. This is a bunch of line segments, that is the balls objects, and this one is also a balls object. Now when we will do the division, then we will take this whole thing as the denominator, we will take this whole thing as the numerator, and now this is done a blocking. This one is also done a blocking. So this is a CAD block now. This one is also a CAD block now. Now we can do the rotation. It will move at a single way. We can do the rotations, and both the whole bunch will rotate or scale together. After doing the bunching, that is the bunch of line segment, we can think of it as a scalable as a single entity, and similarly this is also scaled as a single entity. Now without understanding these kind of things, mathematicians cannot understand what it is, because without the experience of CAD you cannot understand these kind of mathematical objects with your grasp, with your visualization, because these kind of dynamic movements are visible only to the CAD peoples or for the building information modeling peoples. Normally mathematicians don't get these kind of facilities, so they cannot think of these kind of objects there. Now this one is the denominator object, which is constructed from the single line segment, and the output line segment is like this here in the green color, and similarly this one is the initial line segment for the numerator, and the output line segment is different. Now if we copy it and scale it, or rotate it, we are doing scaling, we are doing rotating, and even after doing all these things, suppose this one is scaled and rotated and this one is kept here. Now this one is kept here. Now if we align this one with the L with L, if we align this L with this one L, then we can align it in 4 ways, but ultimately both will override on one another, because the L are kept fixed, and now the alignment is done, and this alignment is done here, where we can do the reverse aligning also. If we do the alignment, then we can see that the L are overlapping on one another and the line segments are overlapping. In this way, the rotated or scaled objects will get on the same entity, but they can align in the different orders, and we get four different alignment possibilities are there. Suppose this one is aligned, and while we are using the align command on this, the first point is aligned with the second point here, second point is aligned with the first point here, we will get the different alignment of this object, and we will get the objects in the reverse order. But if we do the, now we can think of this bunch of line segments as the mirror of the output, and we can think this alignment in this way also. We can think it as we can think this bunch of line segments as the alignment with the opposite cases. Suppose this one is rotated 180 degree, then we will get this one, and this one looks different from the first, second, and this one is the third one, where the output is like this. And now if we do the mirroring of these 180 degree rotations, the cleans 4 orientations is like this. You will not get the orientations with the 180 degree rotations every time. So all these 4 images are different. Look, the position of the final output line segments locations, the green and the cyan, green and the cyan, green and the cyan positions, and the green and the cyan positions. Here the green and the green position is here, which is overlapped on one another, and you can see that the green and the cyan positions are here. So the 4 options of the gluings are happening, and these kind of bunch of line segment formations are there, and the CAD programmers always face these kind of issues of which one of these 4 possible orientations is to take for a particular kind of situation. So to avoid the ambiguity, we need the names, proper names for every kind of gluing conditions. And you can see almost these 2 things look almost same, but the output line segment positions are changing. And while writing the CAD programming, if you don't express the things properly, look, these 2 things look same, but the output line segments positions are changing. The green positions are visible here, here the green is overlapped on this, and so until we specifically mention which kind of oriented aligning we are expecting, our output can give us ambiguity, and programmers can get the ambiguous result. Your staircase will enter into your bedroom instead of going to the right position. So to get the automated generations, and if we try to do the perfection with the artificial intelligence, then it becomes more challenging, because the artificial intelligence models are doing everything inside it, and human beings are not monitoring it continuously in the unsupervised learning systems, and the chances of ambiguity increases too much, because you don't have the control until you keep the proper operators naming for every kind of orientations as per the journey objects. And vectors will give you the confusing outputs, because for every vector there are 2 possible journey objects, and if you are not mentioning the journey objects on which orientations you are trying to align it, then you are going to get the wrong results every time. Now this bunch of line segments are there. Suppose these are the one is the numerator and another is the denominator. Now when we are getting this bunch of line segments, now we have the numerator constructed from the denominator, and that means when doing the division of this numerator bunch of line segment with the denominator bunch of line segment, then we have to think about the 4 different kind of alignments of the outputs to the outputs. So this is equal to 4 possibilities in the CAD programming. These 4 possibilities of placing the numerator bunch of line segment. Now the whole bunch of line segments are going. The input is here, the denominator's output is the input for the division. Now we are placing the denominator on the denominator output line segment to the numerator input line segment, and then we are putting the complementary line segment here, and then the division of the type 1 is done. In the similar way, we can do the division of the type 2, where we will align this output with this position, and we will connect the free ends of this output like this, and we will get the second division orientation. We will get the different kind of orientation here when we will place the things like this. The input to input is aligned here, and then we will connect the free ends of the two line segments, and we will get a triangle here. All these triangles which are forming, these triangles are forming due to the divisions. These are the triangles generated due to the divisions, and these are the common gluing triangles, where one edge is coming from the input, that is from the denominator bunch of ball subject, that is a bunch of line segments, and another line segment is coming from the output, which is the output line, a bunch of line segments which is generated at the numerator, and these two different bunch of line segments are interacting with their final output line segments, and so the two edges of a common triangle are forming. Now the three are formed, and the fourth one of this division is constructed when we place the output of this, construction differently. Say, so this one is placed at the starting of this, and we are constructing the common triangle here, and you can see these four triangles are looking different, and these four triangles are looking different. Exactly same as this one, and but a difference is that this one is the outer boundary, the outer CN line is on the outer boundary. Here CN line is not the outer boundary. So if we consider it as the periphery beams, if we consider the things as the periphery beams for the roof plan or for a building third floor plan or sixth floor plan, then the periphery beam finding is the issue due to the divisions and which kind of line segments are going where. These are very important because these are the beam placements for any bridge or for any building, and we can get the four different kind of orientations due to the divisions, and the divisions are going to give us the bunch of line segments division with a bunch of line segments here. And now we will discuss about the plus and minus also, and for doing that we have to discuss about the caliberness objects, and stay tuned, we will discuss about the plus minus also. The multiplication and the division are there, and there is a separate video on the multiplication is doing, and now we are discussing about the divisions, plus minus, and the order operations also. These are very important subjects, and one more thing here is that these geometries generate the music, and that music you are listening. We have discussed division of four possibilities when a GT simplex is divided with another GT simplex, and GT simplex is generated with pure multiplication, where the triangulations are formed like the glued objects of the triangles. The input and the outputs are both the glued forms of the triangles, and these are bunch of line segments because these are the CAD blocks or any parametric blocks, and which are controlled with the 6 angles theta 1, theta 2, theta 3 like this, and which selects together the bunch of line segments means the blocks and which selects together, and when we click on a single point it will come together and we cannot separate it. And the bunch of line segments is a very important subject, because until the people in the CAD use the CAD, they cannot understand that the bunch of line segments behave in this way, where the bunch of line segments behaves like this, where when rotating they rotate together, when scaling they scales together, when translating they translates together, like this. When copied they are copied together, and like this. These are the bunch of line segments. Bunch of line segments means either they are constructed with the pure multiplication or pure division or due to the plus minus. Now I want to show you that how the plus and minus works. Suppose this one is a bunch of line segment, this one is another bunch of line segment, and now we are doing the addition subtraction kind of thing. Now all of the kind of bunch of line segments that we see are constructed with the single initial line segment L. Say we want to show you here that whatever the bunch of line segments we are constructing, they are all constructed with the single line segment, say this, and where the line segments for all the part of the trigonometry expressions, every part of the trigonometry expressions are constructed with a single line segment, and which are constructed in any order in any way, but the initial line segment remains the same for all the parts. Say for the expressions we have discussed here, the zoom extends. Say here we can see several terms are added, several terms are multiplied here, and these summation symbol, multiplication symbols were done by Euler. They were introduced by Euler in 1740 to 1760. Suppose whatever we are doing, every part of the trigonometry expressions are constructed from the single initial line segment L. So suppose the 3 sin theta, this sin theta is constructed as the L taken as the hypotenuse. This sin cube theta is also constructed with the same L taken as the hypotenuse. This sin 3 theta is also constructed with the same L, but after transforming the fx changes. And these kind of constructions are used for our construction in the API developments in our companies, or also in our industry, where we are using the Tekla developments and implementing the Tekla constructions for our users. We try to understand how to think about the translations and rotations and orientations, as our users always get confused that which one to take at what conditions, because every time it is not possible to demonstrate the juniors that which one of the journey objects we have to consider for what kind of developments and what kind of staircases we have to take care properly. These kind of demonstrations are necessary, otherwise the programmers make mistakes and artificial intelligence systems also make the mistakes, and these mistakes ultimately carried forward towards the bigger mistakes, and the whole thing becomes a chaos. And to avoid these kind of errors, we need the non-ambiguous terminology. We need to use the non-ambiguous operators, such that which kind of plus, there are 4 types of plus, 4 types of minus, 4 types of multiplication, 4 types of division, and the different kind of operators give us a different kind of gluing, different kind of arrangements of the triangles. You have seen already here that the different kind of geometries are constructed, different kind of bunch of line segments are constructed, and for every operator there are 4 possibilities open up. And so for every plus we will get 4 different kind of bunch of line segments arranged. For minus we will get 4 different kind of bunch of line segments arranged, and for multiplication we will get 4 different kind of bunch of line segments arranged. For division we will get 4 different kind of bunch of line segments arranged, and so we cannot say that plus minus into divide is a simple term. So we have to define the plus of type 1, plus of type 2, plus of type 3, plus of type 4, minus of type 1, minus of type 2, minus of type 3, minus of type 4, multiplication of type 1, multiplication of type 2, multiplication of type 3, multiplication of type 4, division of type 1, division of type 2, division of type 3, and division of type 4, because for every kind of cases the bunch of line segments, arrangements, and the alignments all changes. And to make the non-ambiguous terminology, to do the non-ambiguous construction protocols, we have to define the proper naming and proper operators residences to get the right results every time with the consistent output. Otherwise our trigonometric expressions can give us a big confusion every time. Now say we have the similar kind of bunch of line segments here. Now we have this bunch of line segment, and suppose we are exploding it. Now we are taking another bunch of line segment which has the output line segment not here. Say this is due to the stretch command, it is like this, and another due to simplex was like this. And now when the outputs due to simplexes are now added, then its output line segment is at the different place. Say this one is not the output line segment there, this one is the output line segment for the another GT term presented here. Now both are having the same L, and that construction is different because the trigonometry expression was different, and so the entire construction was different, and we can consider this kind of object is to add. Now will it add? The question arises is, will this add together? Now suppose these two are two different terms and we have to add this. We have to add these two GT terms, and which are multiplicatively constructed. And now if we try to place the addition symbol here, then end to end is like this, or we can get the end to end like this. We can get the end to end. We can get the end to end like this. Like this, or we can get the end to end like this. Start to start, end to end, and end to start, end to end in this way. And we can think of these things like the different kind of additions, where you can see the arrangements of the seons like this, and you can get the different kind of cumulative summations like this, where you will understand the behaviors, of the output bunch of line segments in a different way. You can see the 4 arrangements of the seon lines are 4 different type of arrangements. In these cases L has shifted because those are not the good additions. Okay, here we want to say what is the bad addition. Bad addition, because the addition is done but no collinearity is checked, and it is not possible to do the collinearity check, and these kind of additions are called the cumulative additions in Sanjoy Nath'S Geometrifying Trigonometry. Cumulative additions, which are bad additions, but these also give us different kind of picture. Now if these are collinearized, the good addition, that is forced addition, which is not the bad addition but the forced addition, collinearized. How? See here. Suppose two multisimplexes are forced to make collinear. How? This one was not collinear, so we will enforce the collinearization here, and we will do the collinearization of the output line segments, and this is the collinearization done. And for this second case, the collinearization is done like this, and the output line segments are now collinear. In this case, the collinearization is done, and here the addition is now possible. For this case, collinearization is done, and now the addition looks good, and the collinearization is done. And for the two different cases, one was the bad addition, one was the good addition, but the forced addition is done here. For similarly to subtraction, the overlapping will happen. Suppose if we want to do the subtraction in this, then we can get the forced overlapping, forced subtraction, where we will do the forced overlapping subtraction, where we will do the overlapping of the smaller line segments on the bigger line segment. Forced subtraction. And naturally bad subtraction is not possible, because without the overlapping we cannot do the subtraction. Actually, bad subtraction is a odd concept, because bad subtraction is almost impossible. Because non-collinear objects are not subtractable. Forced subtraction with the collinearized output line segments. How? Here one is the bigger line segment output, and another one is the smaller output line segment. How will we subtract that? We will rotate this to make the smaller one collinear on the bigger one, and in this way the smaller one is overlapped on the bigger one, and the remaining part is the final output line segment due to the subtraction, and this one is the final output line segment here, but the whole bunch remains there. Similarly, for the forced subtraction here, the smaller output is rotated. The smaller output is rotated at the common point and overlapped on the bigger one, and we will get the output line segment here, and which one is from here to here, and this is the final output line segment for the subtraction after the combining the things, and you can see it here. For this kind of orientation, we can rotate the smaller one and get it overlapped on the larger one. The output line segments are planned here, and you can see that after doing this, we will get the collinearized outputs. The same way here also, we will take the smaller one and rotate it, overlap the things on the bigger line segment, and we will get the subtraction from the remaining line segments. So the four different types of the subtractions which are done with the forcing, and the collinearized outputs are also shown here. The addition and subtractions causes the locked set. Now this one is a locked set generated due to the plus or minus. The forced addition generates a locked set, and now it is a locked set after collinearizing, and now this locked set divided by another locked set, we can get another kind of division, which is a first locked set divided by another locked set, and ultimately when we get the locked set, then obviously the plus and minus symbols are involved there, and forcing was done there, and the L moves. But what is the good trigonometry expression? Obviously, for the good trigonometry expressions, L don't change its place. I repeat, here you have seen that due to forcing or any other process, the position of the L changes. If things are natural, where the L don't change its position, L remains at the same position, then it is a good trigonometry expression. Sometimes we need to do the permutation over the trigonometry expressions to get the best output of these block sets, where the L never change, and so the outputs looks fantastic, and our trigonometry expression is a good trigonometry expression. Now we will talk about the caliperness. The caliperness. Caliperness is a term that is introduced in Sanjoy Geometrifying Trigonometry. First of all, we have to understand what are the calipers. We have to understand the caliper objects. Okay, so these are the things and which we have known from our school days, where the objects like this were calipers, where these kind of objects are there, where the fulcrum point is here, which are the calipers. These are used as the measuring instrument before the verniers, and these caliper objects are there. So we can think anything as a multi-caliper when it is like this. When it is like this, these are called the multi-calipers, where the fulcrum points are there at every junction, and these kind of things are called the multi-caliper objects, where there are several arms. There are several arms where there are two free ends, and these are the caliper objects, the multi-caliper objects. These are the multi-caliper objects, and we can use these kind of things as the measuring instruments. Now, how to straighten these kind of multi-caliper objects? Suppose these are the multi-caliper objects, and we want to straighten it sequentially. When we have to sequentially multi-caliper it, we have to imagine that we have to explode it first, because until the multi-caliper objects are exploded, we cannot do the sequential straightening. Suppose this was the multi-caliper object, and stretched straightening is like this, the stretched straightening. Okay, this is called the stretched straightening, but when we will do the stretched straightening, this will not get straightened, and these kind of problems happen. These are the stretched straightening is not allowed, and sequential straightening of the multi-calipers. These are the sequential straightening at fulcrums, and these things are done in the geometrifying trigonometry, and these are the effort necessary to sequential straightening in geometrifying trigonometry is the effort for this sequential straightening is caliperness. It's a metric, it's a norm, it's a measure. Now, how can we do the sequential straightening? Take the last one, rotate it about the last fulcrum. We will not use the pivot point, because pivot point is the official term in geometrifying trigonometry, and this is the sequential straightening process. this is the sequential straightening process. One at a time, we are sequentially choosing the fulcrum one at a time, and we are rotating the right bunch of line segments about the right fulcrum point to get the sequential straightening through the sequential rotation. And this is done, which is the sequential rotation of the bunch of line segments which are already collinearized, and these collinearized line segments are generated due to the sequential straightening. I am demonstrating here Sanjoy Geometrifying Trigonometry. This effort is necessary because we have already seen that aligning of bunch of line segments is necessary to do the plus minus operations. Otherwise we cannot do the plus and minus. And sequential straightening is also necessary, where the whole bunch of line segments are taken together to get the edges aligned before getting the final output line segments, which will get the multiplications and divisions. Suppose now I am talking with the multi-calipers with the two different multi-calipers. This is one multi-caliper and this is another multi-caliper, which is the exact copy of these multi-calipers. Now this is, suppose it is a red multi-caliper, it's a cyan multi-caliper, and this one is a green multi-caliper. Say one is the input and the output for the division or the multiplication kind of things. Now we will do the things like this: hold operator on this first and hold operator on this first, because the plus minus into divide everything are sequential and everything are non-commutative, so we do everything sequentially. When we use the hold operator here, that is the first term in the plus minus into divide, when we see plus or minus operators, the first term is hold tightly. This first term, suppose 1 plus cos x plus sin x, there 1 is the first term. If we write it as the cos x plus sin x plus 1, then cos x is the first term. So first term hold tightly at its own place, tightly at its place. Don't move it. Don't move the first term. Don't rotate the first term. Don't rotate the first term line segment. This is the rule, and if you have to rotate the last term. Rotate the last term first. Rotate the last term first about the last fulcrum point, and so obviously cut at the first fulcrum. So cut at the first fulcrum or the well planned fulcrum. That is a tactic, automated theorem prover tactic. Automated theorem provers use tactic objects like Haskell's, like POC, COQ, like ML. Wherever we use the tactic object is used. The tactic is also an effort, and this effort is also calculated in the caliperness object. The caliperness is measured. Caliperness is the total effort of straightening multi-calipers. Effort is equal to this effort is tactic effort plus rotation effort plus holding effort plus sliding effort if necessary plus scaling effort if necessary plus lifting and shifting effort if necessary plus breaking of the fulcrum effort if necessary, and all these kind of efforts are totally added and generated the total measure of the caliperness, and minimum caliperness to achieve the straightening is the best objects. Minimum caliperness is least energy principle, which is best. Now, if for any trigonometry expression you don't have to do any calipering or straightening, if the best written trigonometry expressions are those where you don't have to straighten, where you don't have to straighten anything, where everything are auto-aligned, where all the output line segments are automatically auto-aligned, where all the output line segments are automatically auto-aligned to do plus minus into divide things and automatically overlapped on one another, then and L is not moved at all, and several L are there to construct every balls objects, every bunch of line segments objects, that is the bunch of line segments objects, and all these L, you don't have to move any L, you don't have to move any L to align the output line segments. Caliperness equal to 0, which is best trigonometry expression. So these are the concepts used here, and now I am showing you here the planning of this. Suppose the first term written has a output line segment L here, and total geometry is exploded first. First line segment, that is the first term, is hold tightly. For this different trigonometry expression, the first term is this, and which is hold tightly. The last term representing some output line segment, and we are rotating it to get the alignment here. So we are getting the total for either we can do it anti-clock or clock, and whichever is going to give you the least work and least energy principle is used. Similarly, this one is hold, so we will rotate the last line segment first, either clockwise or anti-clockwise, which gives us the least caliperness, and then we will align it here. Then the bunch of line segments is picked and then aligned with this one, so we get the two output line segments, and now this is one output line segment, this is one output line segment generated from the bunch of line segments. Now we can do the multiplication, division, after doing this crunching, then only we can do these arrangements, and those are in the 4 different ways, and we can get the 4 different kind of triangulations, and we can get this here, the green bottom, green top, green right, green left, and we can get the 4 different kind of arrangements here, and these 4 different arrangements are like these. These are the 4 different arrangements, and after getting these 4 different arrangements, we can now place the third line segment to complete the triangle, and the 2 similar triangles on the left hand side and right hand side gives us the equality conditions for the trigonometry ratios, and caliperness is described in this way. The straightening process, the planning process, and the total effort process is there in the caliperness objects. And now this part is done, and you are at least at a certain position where you can think about the geometrifying trigonometry, where these objects are very important to think, and the 4 ways of aligning, placing the objects is also discussed here. These concepts are official terminologies in the Sanjoy Nath'S Geometrifying Trigonometry. Now we will show you the demonstration of this whole theory in a single glance. We have already talked about the constructions there. We want to show you how the world is thinking. Joseph Austin Bilku are very important persons about the polyhedral constructions and geometric objects. They have also claimed the same kind of things, where the geometric way of thinking is very necessary, and where the non-commutative way of working is very necessary to get the output line segments, and how these output line segments actually interact with each other and generates the 3D objects. In engineering studies, we already study these kind of things, where the line segments and the gluing of objects are important to construct the real geometry for engineering purpose, and unit circles are never discussed in this kind of situation, and visibility problem for the art gallery problems are also those kind of situations where we never see the unit circles are used. Unit circles are useful for the electrical engineers, for the vibration analysis, for the electronics engineers, for signal processing, but for structural engineers and for mechanical engineers, unit circles don't help us. There we need the real triangles, real robot arm movements, and real geometry constructions, where triangles and the gluing of the triangles are mostly important things, and these are also the caliperness kind of things where multiple line segments are in 3D, and we have to straighten these objects to get the caliperness objects, and these objects are there. You can see the real practical industrial applications of triangulations and caliperness for the surface developments, and which we hold on arms, and the straightening of these line segments, the efforts are calculated, and Cauchy arms lemma is also there. These kind of things are taught several times, where we are considering these kind of objects in mathematics for engineering purpose, for mainly for the structural engineering, mechanical engineering, for robot arms movements, for tailoring, for construction management, and to plan for the building information modeling, for CAD programming, and these are important objects to discuss, where you have seen the output line segments from the different bunch of line segments are taken to construct the real geometries in 2D spaces, 3D spaces, or in the higher dimensional spaces. You can see the practical applications here, such that you can connect trigonometry with the real world of ontological basis of triangles. So obviously try to avoid the unit circle methods while thinking about trigonometry, otherwise you will miss a lot about the world. And here it is claimed that the real construction is different thing, and tailoring of cutting of the line segments, straightening of the line segments, making the surface developments, and these construction protocols are really important, and it is claimed that tailoring is finer than sculpting, where it is claimed that if you want to construct the things, sculpting has a different reasoning, tailoring has a different reasoning, and to do the tailoring you have to understand the straightenability of the edges, the caliperness of the edges, how to do the surface development planning, and how to find the edges, how to find the triangles, how to get the triangulations. Otherwise you are not going anywhere to develop the real solutions for real mechanical engineering, for the real construction planning, real structural engineering. You are not going anywhere if you cannot think the things with triangle geometry. So finding the right vector objects, finding the right journey objects is going to give you the deeper understanding about the real world of constructability. So we are starting our presentation on Sanjoy Nath'S Geometrifying Trigonometry, and the presentation starts here. So every line segment interact with another line segment to generate the conclusion. Multiplication is doing, which is already shown, and addition is going to generate the log set objects, where end-to-end adding, end-to-end collinearization is important. And if the natural addition is there, where the natural collinearization is there, then we will get the natural output. Otherwise caliperness increases, and that is not going to give us the best trigonometry expression. In Pythagoras theorem, there are 256 possible geometries are there, where least caliperness is achieved in only few cases, and those are also demonstrated here. The best least energy principle applied out of these 256 configurations is to discuss, and there is a separate video to demonstrate on these which of these have the least caliperness and least energy is used to get the best Pythagoras theorem, and where the output line segments automatically get collinearized and we don't have to shift the initial line segment L. That is also demonstrated in a separate video here. You can get it with the 256 options for Pythagoras, and there you will get those demonstrations where we have shown that in Sanjoy Nath'S Geometrifying Trigonometry how to get the real overlapped line segments, where the addition don't need the collinearization, where the overlapping of the cos square theta and sin square theta always happen on the hypotenuse object, and then the p square plus b square is equal to h square automatically occur, and for some particular operators, and it will never occur for other kind of operators. So these are the 256 options. The left hand side is showing the cos square theta line segments, and right hand side is showing the sin square theta line segments, and when they are superimposed, then we will get the overlapped line segments, and sometimes we will not get the overlapped line segments, and naturally overlapped line segments occur for some configurations. And this is showing that when p star p is collinear with the p star b, then h star s is the best configuration of the multiplication and addition. And L star cos theta is a line segment representing the base, and L star cos theta also represents another line segments on the 2D plane, but 4 star 4 is equal to 16 possible rearrangements are possible, and these are shown with the blue lines. Similarly, the L star sin theta is a line segment represents the perpendicular for a triangle, and L star sin theta also represent another line segment on the 2D plane, and we don't have to think about 3D, 4D higher dimension. On the 2D plane only, all the multiplications of the numbers are shown in the 2D affine geometry and the Sanjoy Nath'S Geometrifying Trigonometry, and but these are generating the 4 star 4 16 possible green line segments, and these arrangements are possible, and these are shown with the green lines. And all blue line segments are not collinear with all green line segments, but 16 star 16 is equal to 256 possible arrangements of the blue line segments and green line segments are there, as you can see. And in the cases here, after superimposition, These are two separately placed things for the cos square theta on the left side, sin square theta on the right side, and these are all represented with the line segments, and these objects change their positions in the GeoGebra file attached in the video there. You can see these line segments reorient and rearrange themselves when theta is changed. That is when the seed angles are changed. You can see that line segments are rearranging themselves, but some of them always overlap on a single collinear conditions, and those always overlap, and every line segments have a proper nomenclature L, A, B, C, D, E, F in this way. In Sanjoy Nath'S Geometrifying Trigonometry, every line segment has a proper address, such that in the machine learning algorithms or in the theorem searching algorithms, we can address the proper line segments, proper triangles, proper points properly, such that non-ambiguous theorem generations are possible. Now, here we are showing that this kind of things give us the best caliperness conditions for some conditions, and we will discuss on those topics in detail. But we will talk about the practical engineering applications with some books data here, which I cite. The citations are here, shown here properly. In structural engineering or in mechanical engineering or for the robot arm planning or surface development planning, the foldability questions are always there. Folding and unfolding are also very important subjects, and subject is well discussed problem and they are open for the engineering purposes, where linkages and folding caliperness are important in straightening issues. These kind of things are the GT simplexes, where the surface developments are normally GT simplex objects, and the robot arm problems are also the log set kind of objects or GT simplex kind of objects as per Sanjoy Nath'S Geometrifying Trigonometry. And some practical applications are shown here, where the straightenability and the rotabilities are always considered. These are the caliperness efforts straightening with the multi-calipers, and these kind of objects you can see in engineering purposes, and I am just showing it for your understanding that in the engineering uses for the linkage mechanism designing, the geometrifying trigonometry has a very big implementation. Before Sanjoy Nath'S Geometrifying Trigonometry, the algebraic structure was not there, but people were doing manually to avoid the ambiguity. But when we have to implement the trigonometry to geometry construction with the artificial intelligence or through the computational methods, then the parser need to have the non-ambiguous systems. The parser need to have the proper operator precedence rules. The hold operator, cut operator, straightening operators are also introduced, because without those things, the machines cannot plan the right fulcrum, machines cannot plan the proper rotation operations, which is to do first, which is to do later, and there are the enumerative combinatorics of the geometry. Enumerative combinatorics over the geometry is necessary while parsing and deducting the trigonometry expressions into the geometry. We are not reducing the numerical values from the trigonometry expressions. In Sanjoy Nath'S Geometrifying Trigonometry, we try to parse ARAC. We try to parse the trigonometry expression strings into the geometries, as we are seeing here in this presentation, and also this kind of things that you can see in the pantographs of railway, automated arms, robot arms kind of things, which are also the trigonometry expressions and rendered as the geometry, and for the different values of theta, it changes its position. And here also in the protein folding problems also, we can model the things with the protein folding algorithms. You can see the caliperness kind of conditions are done in the protein folding algorithms, and where the red lines are showing the best multi-caliper inside the proteins folded objects, and these are straightened to do the proper nomenclatures and finding the genomes data and addressing the genome data. So geometrifying trigonometry is applicable for protein folding problems also. Now we are going deep inside the multi-caliper straightening, and that we have already demonstrated in the video. We are moving towards the deeper understanding of these multi-caliperness to the journey objects. We will discuss discuss about the journey objects, cutting, folding, holding, straightening, fulcruming, and sequential straightening to do the plus minus into divide in the proper way. And also the surface mesh developments are also discussed with these conditions. Now we are going inside the theory's depth. These are the examples that we are showing you first, so that you can connect your mind with the industrial applications, because in today's generation students try to find the real world application first before entering into any subject. So we are showing you here the direct applications of Sanjoy Nath'S Geometrifying Trigonometry in real life industrial uses, and without that you are not going to get the interest, I know it. So now we are hitting your mind with the concept directly from the books, from the Isaac Newton, Descartes, Leibniz, and the try of developing this kind of subject. But at that time computer was not there. If Isaac Newton could have the computer in his hand, then geometrifying trigonometry would come in 1600th century. Not we had to wait it up to Sanjoy Nath to develop it in 2020, or Sanjoy Nath was trying to develop it from 2003, from 1998, then conceived at 2003, then the first light came in 2008, and after that it took long times, and after developing so many software simulators, and at this moment it is sufficiently mature and applicable in the subject. Here you will get in this book, here you will get Newton had a very elegant method for finding the multiple of a given angle, which he used on a variety of occasions in his previously cited letter to Leibniz, and he showed how to carry it out and how to find the cosines of these angles at a very small cost in the computations and one multiplication per step. And Newton proposed the concept of geometry usages to find the multiples of the cos theta and he wrote the letter and at that time while he was developing the calculus, he was trying to do the triangulations of the multiple angles, submultiple angles, to find the formula for the trigonometry. And it is well understood now that this was his dream, that someday he will get the geometric interpretation of trigonometry expressions, but he could not get it because the computer was not there, and it was long time taking for anyone who were trying to develop the triangulations and triangle geometry generation out of the trigonometry expressions. At that time the parser was also not there, and before 1920 to 1940 the modern linguistics was not there, even the structuralism was not there, so it was never understood that regular grammars, the parsing mechanisms are necessary. And Donald Knuth, Alan Turing, von Neumann, they proposed several things. Noam Chomsky regularized several understanding, and Stephen Klein developed the regular languages, the regular expressions, the parser mechanisms were done. Now well-formed formula there. Gottlob Frege defined the concept of the arithmetic and the philosophy of languages, and the new kind of logic after George Boole. The new kind of logic came, and after Gottlob Frege and Bertrand Russell, we are talking in the new kind of languages with the new kind of vocabulary about the parsing of the expressions. Until these things were done, it was not possible for Isaac Newton to develop a parser which can automatically convert the trigonometry expression into a geometry object. So Sanjoy Nath was getting these kind of facilities now, so he could develop these things. Otherwise the idea was there at the time of Isaac Newton also, and the geometry is the reality of the trigonometry expression, and trigonometry expressions talk about the geometry actually. And if we go through the Principia from Isaac Newton, then we will see there are lots of triangles are interacting with each other. The bunch of line segments are actually the talkative objects, and bunch of line segments are talking about the things, and here the dark lines are the cumulative additions of the different triangulations of the line segments. Now we enter into the journey of graphical statics, the book, important book in 1848 to 1860, by Luigi Cremona and Maxwell's reciprocal diagram, where the graphical addition, graphical subtraction, graphical multiplication, graphical division are well demonstrated, and these subjects are taught in engineering courses in first year, but people don't read it that much because they are not too much interested in these kind of theoretical objects until they get the practical money in that. Okay, but Sanjoy Nath has to develop it because he is seeing the right practical money there, because the share market data also have the very large number of fluctuations possibilities, because the 4 possibilities in every kind of cases of the plus minus into divide, that Sanjoy Nath could understand that we have to think mathematics entirely differently, because for every plus minus into divide lots of possibilities open up, and these possibilities of bunch of line segments for the single trigonometry expression are all giving the same numerical value, but the bunch of line segments look very different. That is called the ensemble of bunch of line segments, that is the ensemble of balls as per Sanjoy Nath'S Geometrifying Trigonometry. And after doing the geometry interpretations of plus minus into divide is equal to kind of things, the semantics changes and we can get lots of possibility options of the bunch of line segments. Even this music that you are listening in the background is generated from the bunch of line segments, and this bunch of line segments are like these kind of things, and which you can see, and these bunch of line segments are there which are automatically generated from the trigonometry expressions, and from that the musics are generated and which are having the lots of possibilities, and no one can catch copyright because every music will come out from, there are 1,000 number of possible music can come out from a single trigonometry expressions, then automated creativity is also possible. Now we are describing this graphical statics book with the plus minus into divide. The powers of the numerical powers are done with the line segment operations, and bunch of line segments are everywhere. We are just showing here with the plus minus into divide how to do plus minus into divide, the powers and extraction of the roots, and the Lil's method. You can search Google and you can search the older books there, where the Lil's method was used to find the numerical equation solving for the polynomials, solving for linear equation solving and any other things, and the Lil's method was a very popular method. And the graphical statics, where the multiplication is gluing, is also shown here, and the demonstration is already shown here, where the first denominator is taken as the consumed and generated the first numerator, then the first numerator is consumed in the second denominator, the second denominator is consumed to generate the second numerator, and second numerator is consumed in the third denominator, and third denominator is consumed to generate the third numerator. And these kind of concepts were described in Cremona's graphical statics and in the reciprocal diagrams for Maxwell's, on which James Clerk Maxwell was using at that time in 1860 to 1880, and the Eiffel Tower was also designed with this method, because the matrix method was developed for the structural engineering. The matrix method came after 1910, and during the 1860 to 1890 these methods were used to design the structural engineering things, and these methods were used to calculate the Eiffel Tower problems and the bridges which were designed at that time, just before the Howrah Bridge was designed, before the Rabindra Setu was designed. These kind of way were used to design the bridges, trusses, to design the bicycles, trusses, and these are the practically taken snaps from the books which were in practical use at that time. So don't think that these kind of things are not useful. These are taught in first year of engineering, but people don't take it seriously because they don't get money from that, and because computers are there which do the things, calculations numerically. So these understanding of the GT simplex or the log sets were not necessary before the artificial intelligence came in, and artificial intelligence with the non-supervised learning systems made the non-ambiguous systems, and to give the non-ambiguous plus minus into divide is equal to operators. Sanjoy Nath had to design the non-ambiguous operators to make the AI working for the trigonometrical expression parsing into the geometry. The real geometry are hidden here. Here we want to show is that any text like mathematical formula or text like expressions or the text like mathematical identity or the text like mathematical inequalities in the textbooks are syntax to express the facts of the truth. And we cannot touch these real objects with the hands, nor we perceive any actions or work happening with these text-like syntaxes. So these text-like syntaxes have no right meaning. These are syntaxes. But meaning-making process converts this into the real geometry, which we can construct with the wireframes, which we can construct with the steel, which we can construct with the concrete, or at least as a paper model, such that we can demonstrate it as a really hand-holdable objects. Things are meaningful now when the semantics are generated, and that means when we can touch the objects with the hands, like the bridges, wireframes, roads, buildings, pavements, cranes, machines, working robots, machines, vehicles, etc. These things are semantically, practically, really holdable objects. These are not syntax. So converting these syntax-like objects to the real semantics is important, and to do these things the geometrifying trigonometry is very important. Meaning making process is that things are meaningful now when we can hold it with hands or when we can see the real geometry of the real things there, and these are discussed in this subject. Geometrifying trigonometry, that is SNGT, that is Sanjoy Nath'S Geometrifying Trigonometry, is a new subject to do this activity. What? That is converting the syntax like abstract trigonometry formula automatically converted to the meaningful real geometry. In the height and distance kind of problems, where the real geometry problems or the survey problems were forcefully converted into the trigonometry expressions, that was called the trigonometrifying geometry. That means when you have a geometry problem, you are converting it into a trigonometry problem. That is the trigonometrifying geometry, where the reality is converted into the abstract things. But Sanjoy Nath'S Geometrifying Trigonometry, SNGT, is doing the reverse thing, which is the geometrifying trigonometry. That means from the abstract syntax of the trigonometry formula, Sanjoy Nath'S Geometrifying Trigonometry converts the real meaningful geometry, and the abstract trigonometry formula hides lots of possibilities into a single abstract trigonometry formula. So the lots of possible geometries were hidden there, which comes out as a one-to-many relationship, and one trigonometry formula can give us multiple number of geometric objects. And what are those exhaustive list of geometric objects? Sanjoy Nath'S Geometrifying Trigonometry answers that and generates all these exhaustive list of possible geometries which you can hold with your hand after constructing it with the wireframes or like these things. Now, the textbook trigonometry problems don't show the underlying geometry which are present there. There are lots of triangles present there, lots of different similar triangles present there. Sometimes when the trigonometry expressions only have a single theta or single x, single y, like the things, then it has only one type of similar triangles arranged in the multiple different ways to construct the whole thing, to construct the whole bunch of line segments. So we have to understand the possibilities of understanding different kind of triangulations are hidden inside one single trigonometric expression. Geometrifying trigonometry is the algorithmic system which exhaustively converts the textbook trigonometry problems, text-like formula or text-like expressions, to the real constructible geometry which we can physically construct with steel, metal or concretes. Now, what is mathematics actually? As per Ncert discussions, we get this important talk, that is, the mathematics requires abstraction. It is a discipline in which the learners learn to generalize, formulate and prove statements based on the logic. In learning to abstract, children would need concrete material, tools for visualization, experience and no context as scaffolds to hold them, to scaffolds to help them. What are scaffolds? Scaffolds are those bunch of line segments made up of bundles or made up of those steel frames which are used before the concretes are placed. When the roof casting are done, you have seen that several times in the construction buildings, there are different kind of bunch of line segments, the bunch of steel rods or bunch of bamboos are placed below, on which people stand and on which the roof stands until it is concretized. Those are the scaffolds, those are the helping tools to construct the things. So scaffolds are necessary to understand the abstraction, and geometrifying trigonometry is going to give you the reality in front of your eyes, such that the children can understand, so the students can understand what are the kind of reality hidden inside the trigonometry expressions, and what are the multiple types of possibilities hidden inside the trigonometry expressions. Children are expected to verify principles of the patterns and would also be trying to find out exceptions to these. So, while on the other hand, children would be expected to observe patterns and make generalizations, and they would also be required to identify and find the exceptions to the generalizations and extend patterns to new situations and check their validity. So Nath did the same thing with the trigonometry expressions to bring out all the possible geometries hidden inside the abstract trigonometry expressions, which look like some odd kind of English sentence. The trigonometry expressions are like the syntaxes, which hides lot of geometric possibilities, and no one were searching for these kind of things before Sanjoy Nath. So Sanjoy Nath had to make it such that he could write the application programming interface programs on CAD, and non-ambiguous situations are necessary to construct the staircases or the bridges. So Sanjoy Nath had to design this whole subject himself, otherwise he was not getting the facilities of computer to get the non-ambiguous constructions. Geometrifying trigonometry, a novel, algorithmic, well-formalized approach to generate diagrams, that is a line segment, bunch of line segments diagrams of trigonometry automatically. Our classical trigonometry is ambiguous and full of ambiguity, full of doubts, and what kind of geometries can occur, what kind of alignment can occur, no one knows that. And our classical trigonometry is ambiguous and incomplete and as a theory, and also incomplete as a formal mathematical language, until there is any rigorous algorithmic formalism ready to generate triangles, interactions of the line segments, until there is a subject, well formalized subjects to generate the diagrams, pictures, not the graph like value plots. The graph like value plots are not going to give you the reality. That graph like value plots are like the sine wave or cos wave. These are not going to give you the real construction of the building. So the real construction of building is like the bunch of line segments, or the beams, columns that you see with your naked eyes are like the bunch of line segments, and which are the real geometry hidden inside the trigonometry expressions. That for every given strings, and even this music is also generated from the bunch of line segments. For every given strings of the symbols in any mathematical languages, we cannot say the theory as a complete theory. The symbols, when the symbols are going to give you the ambiguity, that is not the reality. Like before the BODMAS was there, a same expression could give you the multiple kind of answers, and all looks same, all looks good, but some are correct. So the well formal system is very necessary. Operators planning are very necessary. Sanjoy Nath had to design new kind of operators also to make the things non-ambiguous. Sanjoy Nath had to design the order precedences also, the operator precedences also, like the division has to do first, the bracket has to do then, and the division has the 4 types of options, multiplication has 4 types of options, plus has 4 types of options. In this way, even equality also has the 6 types of options in Sanjoy Nath's geometrifying trigonometry, so that which one to take for what condition, that you have to know, otherwise you are going to live inside the whole world of ambiguity. Now every trigonometry expression has a valid well-formed string, and which is attached with a well-defined evaluation function. That is, we do evaluation, that is evaluation function, and that can parse these expressions to the numerical values. But numerical values are not going to help you every time, because the numerical values are not going to give you the pictures. The numerical values are the length of the final output line segments, but that is not going to give you the picture of the scaffolding. It is not going to give you the picture of the beams and columns. It is not going to give you the pictures of the triangulation. So numerical value is not helping. So evaluation is not going to help you for every cases. But the numerical values cannot describe exhaustive details of all possible pictorial geometries of the several non-ambiguous, well named symmetries hidden inside the kind of mathematical expressions, parsable strings of the symbols to the directly usable meaningful objects. To make our classical trigonometry expressions to more intuitive and directly usable as a diagrams, there is the scaffolding of the line segments, there is a bunch of line segments of the arrangements, and the multiple possibilities are there of the real triangles, and we need the well-defined algorithm with well-defined proper plus, proper minus, proper into, proper divide, proper equal to, which kind of these operators to use to get which kind of real bunch of line segments is very important, and that algorithmic framework, and which we call the e-picture instead of evaluation, we call it the e-picturization. That is, it generates the pictures, it generates all possible pictures, and these are given trigonometry expressions to the real geometry of the triangulations in the CAD files, in the true scale, and also in the SVG files, in the true scale or the CNC files, which we can directly cut in the machines. Until we are getting these kind of outputs, that is the abstract thing, that is not the reality. So we were searching for the algorithms and the simulators or the process to read the trigonometry expressions and to generate the real geometry of the bunch of line segments, which we can really construct with the steel, with the construction materials, or with the wireframing models, which we can hold with our hands. So the reality is a different thing and valuation is a different thing. Geometrifying trigonometry is the endeavor to parse or convert all trigonometry expressions which are abstract and to the concrete objects and identities, inequalities into the shapes, figures meaningfully automatically through some forms of the string operations. String operations is the term used while the first parsers or the compilers were designed, when the regular expressions were designed, when the context-free grammar was designed, when the regular expressions were designed, regular languages were designed. At that time, the string operation, stringology, was the terms that came during 1920 to 1960, when the computers manufacturers were designing the operator precedences and the nature of the parsing mechanisms, the algorithms designing for the Fortran or the basic C BCPL languages were under construction. At that time, these string operation terms was very much official. And through the computation, if we try to do anything through the computation, then the string operations, the parsing, lexing, compilations, and these are all kind of the string operations. Even the language, the grammar, these are the string operations, the rules on the syntax to generate the semantics, or the semantics to syntax. These journey are the part of the computer science and structured linguistics. Now we are talking about the Thales theorem, where one line segment is given, then we can draw 4 different ways of cos theta, 4 different ways of sin theta, and this picture is showing you that all these 4 options are equally valid, but giving the same numerical value of cos theta, same numerical value of sin theta. So the evaluation principle is not going to give you the right answer, because the journey object is important. For every numerical value, there are 2 possible vectors, the go vector and the return vector. And so for every numerical value, the one line segment is there, and 4 journey options are there. On the left window journey for the go vector, left window journey for the return vector, right window journey for the go vector, and right window journey for the return vector. In that way, we can think about the 4 journey objects for everything, for every number. Now, how to think about these objects? There are 4 types of cos theta, A, B, C, D. In this picture, you can see when L is given, then here we are showing that L, then cos theta of type A, sin theta of type E, cos theta of type B, cos theta of sin theta of here is the cos theta of type A, here is the cos theta of type B, here is the cos theta of type C, and here is the cos theta of type D. And for the cos theta of type A, we get the complement line segment as a sin theta of type E. If the output is sin theta of type E, then the complement line segment is the cos theta of type A. In this way, in Sanjoy Nath'S Geometrifying Trigonometry, for a given hypotenuse L equal to 1, we get 4 different cos theta A, B, C, D, we can get 4 different sin theta E, F, G, H. In the similar way, in Sanjoy Nath'S Geometrifying Trigonometry, when L is a given line segment, and where tan theta of type I, tan theta of type J, tan theta of type K, and tan theta of type M are there, and similarly sec theta of type N, sec theta of type O, sec theta of type P, and sec theta of type Q are possible. These are the 4 journey options, and sec theta is the complement of tan theta, and tan theta is the complement of sec theta. When we generate the output as the tan theta, then sec theta is the automatically generated complement, and in that way we think in Sanjoy Nath'S Geometrifying Trigonometry. Now here N, O, P, Q are the 4 types of sec theta, I, J, K, M are 4 type of tan theta. And similarly for the cosec theta, you can see that cosec theta is the hypotenuse, which is a complement of the cot theta, and when L is given, then we get the cosec theta and cot theta in this way. Like there are, when the tan theta is like this but cot theta is like this, when we take the L as a base, then we get the perpendicular as tan theta, but when we take the L as the perpendicular, then we get the base as the cot theta, and we get the hypotenuse as the cosec theta. So the denominator is consumed as a hypotenuse or as the base or as the perpendicular, and the numerator is output as the hypotenuse, base, or perpendicular. In this way, the different options open up in trigonometry, and those are the 6 different ratios, and where two complements are there. For the cos, the sine is the complement; for sine, the cos is the complement; for tan, the sec is the complement; for sec, the tan is the complement. Similarly, for the cosec, the cot is the complement, and for cot, the cosec is the complement. These are the understanding there, and 4 options open up for everything. Now we can do the orientations principles also. The triangles are drawn from the P, S, N, like the P is the pivot point, S is the stretch point, N is the nodal point, and in this way 8 orientable conditions are there. That is, we can draw the line segments in different orientations, and in this way the 8 different orientations are possible, which are shown here. That is the PS, that means the pivot to stretch, SN means stretch to nodal, NP means nodal to pivot. In this way, PS, SN, NP, PS, SN, PN, PS, NS, NP, PS, NS, PN, SP, SN, NP, SP, SN, PN, SP, NS, NP, SP, NS, PN. These are the 8 kinds of orientations possible for a triangle construction, and so these also give us a different non-ambiguous situations for the triangulations generation. And whoever works with the finite element methods, they know the triangulation process is a very tedious process, and where ambiguity is everywhere. To make the things non-ambiguous, we need a concrete understanding for the triangles orientations, and the triangle construction orientations are very important subjects there, which opens up the concrete topology. And when we search geometrifying trigonometry, we get these kind of things. Now these things are well known in our textbook, but we don't know when to use the cos theta, when to use the sin theta, when to use tan theta. So geometrifying trigonometry tries to explain everything non-ambiguously, that when to choose cos theta, that means when hypotenuse is consumed and base is constructed, then we use the cos theta, and when the same hypotenuse is consumed and we construct the perpendicular, then we use the sin theta. Similarly, when that same line segment is consumed as the base but we construct the perpendicular, then we use the tan theta, and when we consume that line segment L in the denominator and consume it as a base but generate as the hypotenuse, then it is sec theta. Similarly, when we consume the same line segment L as the perpendicular of our triangle, of the same triangle, similar triangle oriented in a different way, and we want to construct the base, then we use the cot theta. And when we consume the same line segment L and as the perpendicular and construct the hypotenuse of the triangle, then we use the cosec theta. These are the important understanding for the trigonometry learners everywhere. So which one is the given line segment and which kind of objects we are trying to prepare, that is important. Suppose the theta is here and 90 minus theta is here, which means the theta is here also, this angle is here. So when L is given and we want to construct the hypotenuse, then we use sec theta here. When for the same L we want to construct the perpendicular and the base, and when we consume this L as a base, then constructing perpendicular means using tan theta. Taking the same line segment as the perpendicular but constructing the base, then we use the cot theta. And when we take the same line segment L as the base, as the perpendicular, and trying to construct the hypotenuse, then we use the cosec theta. So consuming the same line segment but constructing the hypotenuse and hypotenuse, when we are consuming this line segment L, suppose in our childhood days when we were going to the school and we are taking money for eating tiffin and we are consuming it as the ice cream eater, so we are using the money for a different purpose, that is the black money. So actually when we receive money, we take it for one purpose and we consume it for other purpose. Suppose this L is a hypotenuse of a triangle. Now we want to use it as the non-hypotenuse. Suppose this L is the hypotenuse. Suppose we are consuming it as this L as the hypotenuse and constructing the base, then we use the cos theta. Taking the same line segment L and we are consuming it as a hypotenuse to construct the base, then we use the cos theta. And taking the same line segment L and consuming it as a hypotenuse and constructing the perpendicular, then we use the sin theta. Consuming the same line segment L and we are consuming it as a base and constructing the perpendicular, then we use tan theta. Consuming the same line segment L and consuming it as a base but constructing the hypotenuse, then we use sec theta. Consuming the same line segment L as the perpendicular and constructing the base, then we use cot theta. Consuming the same line segment L as the perpendicular and consuming it as a perpendicular but constructing the hypotenuse, then we use the cosec theta. This is a very important understanding, that how are we consuming the line segment, taking it as the denominator and constructing what kind of line segment there. And you can see when we are consuming L as the line segment hypotenuse, when we are constructing the base as a cos theta, automatically the complement line segment sin theta is generated. Similarly, when we are consuming the same line segment L and consuming it as the base and constructing the perpendicular, then automatically the hypotenuse sec theta is generated. So tan theta and sec theta are complementary to each other. In the same way, when we consuming the same line segment as the perpendicular and constructing the base, then we are using cot theta and automatically the hypotenuse is constructed, which is cosec theta. These understanding are necessary, and this only one orientation is shown here, and where L is not moved at all. This is a very good kind of trigonometry expression where it covers all of the trigonometry ratios together, where L is kept fixed. But if we had to move this L to make the collinearization, here you can see the cot theta and tan theta are collinear automatically. Here you can see that sec theta, cos theta, cosec theta, sin theta are constructed in such a way that cos theta and sec theta are always collinear. For this condition, the cosec theta and sin theta are parallel, and these kind of things are very good to understand. In the similar way, here you can see the gluing operation is done. Suppose when L is given and it is consumed as the hypotenuse and the base is constructed, that is the cos beta, and this cos beta is now the hypotenuse of the second triangle, and where this cos beta is consumed as the hypotenuse and another base is constructed, so it is written as the cos alpha cos beta, but it is wrong. We should write it as the cos beta cos alpha, because this cos beta is done first, then it is consumed in and as the hypotenuse, and this cos alpha is constructed. So this term cos alpha cos beta is the wrong term. We should write it as the cos beta cos alpha. In the similar way, the cos beta is done first, then the sin alpha is done here, so we should write it as the cos beta sin alpha. This is the mistake in the Wikipedia, and we have to ask them to change this orientation, because this orientation or this multiplication order is important, and this is showing us a wrong picture here. We should write it as the cos beta sin alpha instead of sin alpha cos beta. And similarly, from this L, which is consumed as the hypotenuse, and then the perpendicular is constructed, that is sin beta, then this sin beta is consumed as the hypotenuse and the base is constructed, so we should write it as a sin beta cos alpha instead of cos alpha sin beta. This is a mistake in the Wikipedia, and Sanjoy Nath has already asked Wikipedia to revise this. This kind of understanding is very important, because the multiplication is non-commutative and we have to understand these things there. And this one is the sin beta done first, then sin alpha is done, so it should be written as the sin beta sin alpha. And in this way, we should think the single line segment given which has the different gluing effects, and one line segment is always common here. When the multiplication is done, this is the gluing effect, so multiplication is gluing. Whenever we get the multiplication of the ratios, that ultimately talks about some common line segment there, which is the gluing line segment, and without this gluing the multiplication is not possible. So multiplication is gluing, which is described in the different pictures, where the multiplication is gluing. Whenever two triangles are having with the single line segment, common line segment is there, then there is a multiplication, and this multiplication is gluing. And we have to understand the multiplication is gluing means the two triangles are glued to generate the multiplication effect, and that is important to understand. And the GT simplexes are formed with this way. Now the different ambiguity occur because the orientation of constructions are there. We have shown that the position of the one are changing in different cases for the same picture. Here we have shown you that we can get the go vector, return vector on a same train and sitting on the different seats. If the neck rotation is not allowed, if you are not allowed to see backward, then you can see multiple views if we sit in the different positions on the seats on a train, either in the going direction or in the return direction. So 4 possible journey objects in the 2 dimensions are there, and for the journey we can see these ambiguities are there, and to avoid these ambiguities we can think it in this way. And this is a simulator of Sanjoy Nath'S Geometrifying Trigonometry, with which you can visualize the options there. These are the journey objects demonstrated here, which we are talking about for a long time here in this video. And so when we are thinking about these pivot points, stretch point and nodal points, hypotenuse, base and perpendiculars are discussed here, and the GT simplexes, orientations, locked sets are there. And in this way we can think that when the pure multiplication are there, then this part are the GT simplexes, and when the addition are done, then it becomes a locked set. And here the GT simplexes are there because pure multiplications are there, but here the divisions and plus minus are also involved. They are the locked set objects, because the locked set are generated due to the plus minus options. Ontologically, unit circle is not the subject of trigonometry. It generates after Descartes' coordinate geometry, Triangles only. Geometrifying trigonometry starts with the concept that we will not talk about the unit circles as the first place. We will talk about the triangles, triangles, and triangles. In this kind of expressions where we see the triangles are involved in the trigonometry, and we have to count the number of triangles present there, we have to count the number of similar triangles present there, we have to count the total number of line segments are involved in the trigonometry expressions. Suppose there are the divisions, there are the multiplications like the squares, there are the plus minus kind of things, and whenever we will see these kind of expressions in the trigonometry expressions in our school books, then we have to think about how many triangles are there, how many similar triangles are involved there, how they are interacting with each other to justify this kind of formula in the trigonometry. And if we cannot justify the trigonometric formula with the triangles, then we are not doing trigonometry, we are doing something else. So the ontological basis of trigonometry is the triangles, and we will talk about the triangles. Here we can see that the unit circle is shown, but that is not the reality. This was the concept of Euler in 1740 when he tried to express it in the creative way, but to represent that, he defined the 1 as a radius here, and this 1 is not always taken in the same line segment everywhere. Here you can see, here in this picture you can see that 1 is taken somewhere else. Here you can see the 1 is taken at somewhere else. Here you can see the 1 is taken at somewhere else, and here you can see the 1 is taken at somewhere else. But some other deeper properties are present there. When we decide the 1, that is the L, that is the given line segment, and given line segment L is the initial starting point for doing the trigonometry, we should think it in that way, and we will describe here that how to think about L is equal to initial line segment is equal to 1, and from that we will derive all the things in the trigonometry. And we will not derive it, we will construct the triangles out of those things. How will we construct? Suppose there is a triangle like this, and suppose there is a triangle, say this is the L, say this is the L, whatever the length it is, and we have taken it as the L, and we take it as the L with the line color red, and it can become hypotenuse, it can become the base, it can become the perpendicular, depends upon the conditions on which we are thinking about. Now, whenever any number, whenever we see any number, whenever we see any real number, then consider it as the length of any line segment. Say it is the length of any given line segment in the affine space where the coordinate is immaterial, and suppose we can rotate it, we can scale it, but the concept remains same, so it is the affine space. Now length of the given line segment, either this line segment length is less than 1 and greater than minus 1, either it is less than minus 1 is less than this number, or plus 1, either it is like this, less than equal to or equal to this, or it is greater than minus 1 and less than infinity, or it is greater than plus 1 less than infinity, or it is less greater than minus infinity, and whether it is greater than minus infinity or less than plus infinity, it can happen like this. We know that the tan theta we can represent any number which is greater than minus infinity and less than plus infinity. We can represent it as the tan theta. We can represent it as it is tan theta or sec theta or cosec theta or cot theta. So these kind of numbers are universally represented as 4 ways of representing. These are 4 ways of representing. Similarly, for the cases which are of this type, where these are minus 1 to plus 1, then we can do it as a tan theta, cot theta. We can take it as a tan theta or cot theta, or as the sin theta or cos theta. These we know from our school days. So any kind of things we can represent in 4 ways, either in the sin, cos, tan, cot, or we can represent it as the cosec, sec, tan, cot. So whatever the condition it is, we can represent the things like this, and we should not bother about several kind of conditions. 4 ways are possible, and we will show in our demonstration that any line segment is possible to construct as the 4 types of triangles. So we can see it 16 ways of representing any number, 16 ways to represent any number, that is the 16 different triangles, 16 triangle orientations are possible for every real number. And similarly for these cases also, we can think there are 16 different ways to represent any number. Now we will demonstrate how to think about these orientations and how to think about these objectives. Here we are preparing a presentation for students such that we can understand the things there. Suppose we have the Pythagoras theorem, which says that perpendicular is multiplied with the perpendicular and the base is multiplied with the base. Then we are getting hypotenuse over hypotenuse, and this star operation is ultimately the gluing of the triangles, and the addition is the aligning of the line segments end to end. First I should demonstrate that here. Suppose I have a triangle like this. And the seeds angle is theta. Now we know that this point where the hypotenuse meets with the base is the pivot point, because many theorems are dependent on these names. So these are official names. This one is the stretch point, where the base meets the perpendicular, and this is the nodal point where the hypotenuse meets the perpendicular. So these official names are used in Sanjoy Nath'S Geometrifying Trigonometry, because without these names we cannot define several theorems. As we have seen that in our classical trigonometry, the names of the line segments are very official, and these names are official because we need these names to represent several theorems. Suppose if we had no such names, hypotenuse, base or perpendicular, then how could we describe new things in trigonometry? Official names are very necessary to represent the theorems. If the official names are not there, then defining the theorems are tough. Whenever human beings try to do new kind of endeavors, they always try to define some names first, otherwise doing the reasoning becomes tough. Whenever human beings try to do new kind of reasoning with any kind of new activities, then it is very necessary to represent things with some names. Like in geometrifying trigonometry, several terms are there like pivot point, stretch point, nodal point. These are necessary because theorems in geometrifying trigonometry deals with the number of triangles, numbers of line segments, and the bunch of line segments aligning with each other. And the color codes are also very much important in geometrifying trigonometry. The hypotenuse is colored with red, the base is colored with blue, and the perpendicular is colored with green, such that we can discuss about several situations and which kind of line segments is overlapping with other kind of line segments. We need to discuss this kind of situations in different kind of theorems, and to do that we need the proper nomenclature for our understanding. Suppose we have made the block here. Suppose we have made the block here as a single block to make the gluing effects easier. Now we are copying it, and if we copy it, if we scale it, if we rotate it, the similarity property still holds. Even if we scale it, even if we rotate it, the similarity property don't change. So whenever we say the left hand side is right hand side with a 1 ratio on the left hand side, that is a numerator 1 divided by denominator 1 divided by the denominator 1, and there is a division symbol here. That means we will not think it as the number divided by number. We will think it as some input line segment is consumed. This is the input line segment. This is one input line segment. Denominator is an input line segment, and this is consumed, that is eaten by some trigonometry ratio, and it generates another output line segment here, and that is the output line segment. Is generated here. So we can think that any trigonometry ratio is actually consumes denominator line segment and creates the numerator line segment. We have to interpret the trigonometry ratios in this way in Sanjoy Nath'S Geometrifying Trigonometry. Whenever we will see the division symbol is there, that is, whenever we will see there is any number divided by any number, then we will think that this number in the numerator is the length of some line segment, which is the output line segment, and the denominator number represents the length of some line segment, and which is the input line segment. Suppose this is one input line segment, this is another output line segment, and now we can place one common point here, and we can construct a third line segment, and we can construct a triangle. And the left hand side, suppose this one is a left hand side triangle and this one is the right hand side triangle, and we can think it as a scaled form of the same similar triangle. We can think it of as the rotated form of the same similar triangle, and in that way we can say that these two ratios are equal. So which means the two similar triangles are involved there. Whenever one ratio 1 is equal to ratio 2, suppose the left hand side ratio is equal to right hand side ratio, then we will think these two ratios represent the two similar triangles present there, and whatever the scale, whatever the rotation are there, these are the similar triangles, and we are talking about the similar triangles there. So whenever the same seed angle is involved, suppose there is a same seed angle is involved, suppose there is a seed angle theta, and here is also the seed angle theta, and they are in the rotated form or in the scaled form, the ratio remains same. The ratio remains same. So the ratio equality is conserved. We can think the trigonometry expressions like these whenever the ratio forms are there. Otherwise, multiplicative forms are there, additive forms are there, and we will talk about those things there. Since trigonometry talks about the ratio in the first, so we are talking about the ratios here in the first hand. Now whenever we will see that there is a ratio in Sanjoy Nath'S Geometrifying Trigonometry, we will consider it as the denominator is consumed and the numerator is constructed and the third line segment is generated. We can generate this in 4 different ways. Suppose these are the input line segments and the output line segments. Suppose I should write here which one is the input line segments, input line segment, and the output line segment. We should write here that it is the input line segment and the output line segment, so that you can understand the concept clearly. We can think this as the output line segment here, and this one is also kept aligned here with this, so that we can describe the things properly. Now, how can we align these things? Either we can, this one is the output line segment. So now we can bring this here, we can bring this here, and we can join the line segment, we can join the third line segment like this, and we can complete the triangle. Similarly, when the input and output are found, then we can join the output line segment like this, and we can join the third line segment like this. We can do the operations like this. The output line segment is joined here, and we can think the third triangle, possible triangle, is constructed like this. We can think that due to the division, this output line segment is aligned like this here, and the third complement line segment is constructed like this. So we can see that while doing the division we can get four different kind of triangles due to the different orientations. While doing the divisions we can get four types of orientations of constructions, and these four different kind of constructions will give us these four constructions give us different semantics. This is the ontological basis of geometrifying trigonometry. These are important concepts for finding the conclusions about the divisions. Now these four ways of the divisions are having the different symbols in geometrifying trigonometry theory. There you can get the symbols for the division. So whenever we will see the division symbols or these division symbols in the trigonometry expressions, we should consider these are of the four different kind of symbols, and we have to replace with the symbol division 1, division 2, divs 1, divs 2, divs 3, divs 4, and these four symbols will do the Cartesian product. Suppose we have of expression like this. Suppose we have any expression like this, cos x divided by sin x, then we will rewrite it as the concept, like we will replace this with this, and so the Cartesian product of cos x divs 1 sin x, cos x divs 2 sin x, cos x divs 3 sin x, cos x divs 4 sin x. So the four different construction protocols are here, and with that we can easily understand which kind of construction that we are specifically saying to do, and different kind of constructions will give us the different kind of conditions, because this and this looks the similar triangles, this and this looks the similar triangles, but the orientations are different. And if we try to construct any staircase, round stair, or any kind of engineering applications, then these orientations are important. So here we are coming back to another condition, that if any line segment is representing any number, say any line segment is representing any number, and when the line segment length represent any real number, then in Sanjoy Nath'S geometrifying trigonometry, that number is either represented as a going vector or as a return vector. Suppose the going vector is the start end to final end, or it is from final end to the start end. So every number is representable as the two vectors. Actually every number is two vectors. Every number has a line segment, every number is a line segment, and that line segment is every number depicts the length of any line segment, any single line segment, up to this point it is okay. But when we try to do the engineering constructions, then we find the problem. Which direction should we take? So Gibbs, Hamilton, Cayley defined the concept of the vector During 1860 to 1920, the concept was finalized, and Clifford, Coxeter, Hamilton, Cremona, Maxwell, Cremona, Gibbs, and these mathematicians defined the concept of the vector and quaternions such that one line segment becomes the two possibilities. So one line segment turned into two possibilities. One line segment turned into two possible vectors during 1848 to 1920. But after CAD came and when the automation programming started, Sanjoy Nath had to think about many kind of things, otherwise you have to write the million number of if statements to control the geometries. Vector is not sufficient there. So Sanjoy Nath had to think about a grammar. Geometric grammar was necessary to represent the right configuration that we have to use while developing the application programming interfaces for the CAD, while writing the Lisp programs, while writing the C# programs, or while using the mathematical programming for the CAD engineering or for Tekla engineering or for building information modeling. Then the confusion starts is which journey of the vector should we check. Suppose you are sitting on the left hand side of the window in a car or in a train, then you are going to face a problem. Suppose here we want to show the conditions of practical applications while writing the programs or writing the protein folding conditions. We have to think about the orientations on the sides on which we are sitting on a train or on a car. That is important, because without understanding the side of the visibility, you cannot write several kind of programs in BIM, because in BIM, building information modeling, the direction of the vector plus the side of the view is also important. If you are checking in the first angle projection or in the third angle projection, you have to define from which side you are looking the object while constructing or while demonstrating or while preparing the CAD object. Then you should mention, is it a first angle projection or the third angle projection, or on which side you are sitting on a vector. Suppose this train is going from my side to away side, and there are two options: either you are sitting on the left hand side or you are sitting on the right hand side. If you are sitting on the left hand side, you will get some kind of views. If you are sitting on the right hand side, you will get some other kind of views. Now, if turning back of your neck is not allowed, then if you are sitting on this window, you will get some kind of view, and the person sitting opposite to you will get the different kind of things, because the turning your neck is not allowed. So on the left hand side, only things coming in front are visible from one seat, and whichever things are went back will be visible from other seat. Similarly, when you are sitting on the right hand side also, then also you are getting the two different options. Either you are getting the things visible which are coming from the front, or either you are seeing the things which has already passed. The train moving along a vector has the four possibilities, but okay, we are making a simple thing simple, that either you are looking everything on the left hand side or everything on the right hand side. Any constructions happening on the left hand side are on the left of the vector. Any constructions those are happening on the right hand side are on the right hand vector, right hand side of the journey. Now the journey object is necessary, because for every vector, either you will see the origin of the coordinate space is lying on the left hand side of the 2D plane or on the right hand side of the 2D plane for that vector. So in practical applications of engineering, it is very important to know that on which side the other next things are constructed, or already constructed triangles or already constructed points are on which side of the vector. Either it is on the left hand side or on the right hand side of the vector. Okay. So practically, whenever we are doing the engineering application programming interfaces developments, on those situations, the go vector, return vector is not going to give you the complete picture. You have to mention the journey object also. So up to 1920, these kind of problems were not there for the peoples, because they were not having the computers at the time. And after 1960, computers came, and after 1980, the computers became more popular. After 2020, the AI has also appeared, but this AI is also, artificial intelligence is also stuck at some places, because mathematics is not matured, and mathematics is not providing some ground frameworks to the artificial intelligence programmers, such that the vectors are becoming less relevant and journey objects are becoming more relevant. And Sanjoy Nath suggests that there are 8 types of possibilities necessary, but currently up to now 4 possibilities of journeys are defined. Left hand on go vector, right hand on go vector, left hand on return vector, and right hand on the return vector. So every numbers are now becoming the 4 possibilities as the 4 journey objects. And while driving a car also, you need the mirror. If you don't have the mirror, sufficient number of mirrors, then it becomes difficult to drive, and you need to check the 4 possible options while you are driving. The left hand coming things, right hand coming things, left hand past things, right hand past things, because someone is trying to overtake from left hand side, someone is trying to overtake from right hand side, and obviously in India and in Delhi, every kind of road traffics are there where people can overtake you from left hand side, either they can overtake you from right hand side, and you don't know what are the things going on the roads, especially in Delhi, in India. And if you have to make a car which is intelligent enough to decide from every possibilities, when it is a driverless car, then you have to decide for all the possibilities for the things, and vectors are not going to help you. So the journey objects are very necessary to design the artificial intelligence things. One more thing here is the gluingness. Suppose here you have seen that length equal to 1 is taken here, and 2, 3 different triangles are glued. These glued form of triangles are ultimately showing you the representation of the multiplication. Unit circle is not going to give you the answer for these kind of things. Suppose from this Wikipedia page I am trying to explain you, and you will get these kind of pictures in your school days geometry books also. Suppose if the 1 is taken here, and the first triangle is constructed like this, the cos beta, sin beta, and here alpha and beta are 2 different sides angles. Note it. Since the 2 type of sides angles are here, so 2 different kind of similar triangles are involved here, and alpha plus beta is also there, so third similar triangle is also involved there. So from the given trigonometry expression sin alpha plus beta or cos alpha plus beta, every school student should understand that 3 different kinds of similar triangles are involved in this trigonometry expression. One triangle is having the sides angle alpha, the second similar triangle is involving with the sides angle beta, and third similar triangle involved is having the sides angle alpha plus beta. In this picture it is sufficiently clear. Here also 3 different sides angle are involved. One is alpha, another is beta, and another is alpha minus beta. So 3 different kinds of similar triangles are involved in this expression. And these kind of questions are never asked in any school exam where you have to count the number of similar triangles from a trigonometry expression. These kind of questions are regularly asked in Sanjoy Nath'S Geometrifying Trigonometry. So the fundamental basis of geometrifying trigonometry is talking about the counting of the line segments, counting of the similar line segments, counting of the semi-similar line segments, counting of the bunch of line segments, and which line segments is interacting with which other line segment. These kind of questions are discussed in Sanjoy Nath'S Geometrifying Trigonometry, and the nature of the gluing, nature of construction of the robot arms, which are hidden inside the trigonometry expressions, those we will discuss here in the Sanjoy Nath'S Geometrifying Trigonometry. Now coming back here, the multiplication is gluing that I have already shown in the presentation part, where the one line segment is glued on another line segment. I should demonstrate it here on the face, and before doing that I should represent the journey objects here. When one line segment represents on length real number, then it has to represent the 4 journey objects, that is to represent 4 types of journey objects, which are advanced concepts of the vectors. So this is a go vector, suppose this is a go vector, this is a go vector for one line segment. For the same line segment, this is a return vector, and this is a return vector, and we should show these things for the vector here, where the go vector and return vector are represent, and we are showing it here that the line segments as a real number. Then there are vectors possible. One is the go vector, another is the return vector. Now while we are considering about the journey objects, we are representing these go vector and return vectors as the go vector left journey, left window journey, return vector left window journey, which are represented like this. And now we are representing the go vector left window journey, the return vector left window journey. We will represent these like this. The left side window is kept, this is the left window journey, and go vector right window journey, right window journey is represented with the right side arrow only, and return vector right window journey is represented like this. And these representations are the new kind of mathematics, and this new kind of mathematics is necessary to do the new kind of reasoning. Sanjoy Nath has to say here that whenever human being try to do new kind of activity, human being need to do new kind of reasoning, and to do the new kind of reasoning, human being needs new vocabulary. If you don't have the new vocabulary, you cannot represent new kind of symbols. To do new kind of reasoning, human being needs new tools of symbols. These symbols can have different order. These symbols define the arithmetic or algebra, because as per Gottlob Russell, these are logic and new languages and new vocabularies with the new symbols, new languages, and these new languages help us to do new kind of reasoning. And when the new symbol symbols come, like suppose plus, minus, divide were finalized during is equal to also equal to, and several symbols like integration, differentiations and vector symbols were defined during 1460 to now. And one more thing I want to say here, Sanjoy Nath has to say here, that this BODMAS or paid mass came during 1540 to 1650, finalized. And when defining the computer architecture, processor architecture, in 1960, several operator binding rules came, because these BODMAS, PADMAS were not too much important. These parentheses used to help mathematicians till 1960, because machines were not involved. Human being could do all ordering. Humans used this bracket only to manage the first thing first. So operator orders were not important that much. But now, when we are trying to do automation and computers has to decide which operator to do first, now this operator sequence and the operator precedence became important after the automation came. So, and this bracket, the parenthesis, that is the first bracket, is a predicate detector as per Frege 1870 to 1920 developments, as per the philosophy of maths and as per the philosophy of arithmetic. And these are the predicate deciders, and these bracket off means the predicate calculation operators, and that was helpful at that time, and now also it is very important because this bracket decides several things, and operator precedence is also going to come. I will describe here in the Sanjoy Nath'S Geometrifying Trigonometry how to handle with these journey objects and how to handle with these operator precedences to